Now let us establish the equivalence between 1 and 3, which means the strong form or the PDE form and the virtual work form. Okay, so we start with 3, and if we reach 1, that will prove that equivalence. So we start with 3. Okay, so this is the virtual work form which we had derived previously. Now you may proceed either by integrating by parts or alternatively considering that this u comma x times v and whole comma x, this can be written using the chain rule as u comma x times v plus u comma x v comma x, and this second term is what appears in this integral here. So this from here we can replace there. Okay, so what we have is this first integral becomes integral 0 to 1 u comma x. So basically this comes here and this comes here with a minus sign. The other two terms remain the same. We don't do anything to that. Okay. Now this is a whole derivative, so it will integrate out. So this integrates out. Okay. So u comma x at 1 times v at 1 minus u comma x at 0 times v at 0. Now this u comma x at 1 you may recall is equal to h. Okay, and this will cancel out with this term here which we had from earlier, and this second term which is u comma x at 0 times v at 0, here v at 0 will be 0 because u at 0 is a Dirichlet condition, and because of admissibility reasons v at 0 must be 0, and hence this term goes away. So what we are left with is this. Okay, so what we have is integral 0 to 1 u comma xx plus L, this entire thing multiplied to v, and this entire thing integrated over x from 0 to 1 is equal to 0. Okay, now from here we can claim that if this integral is 0, that is possible only when the integrand is 0, which means this is 0, and this comes from something called the fundamental lemma of calculus of variations. Okay, and it is also easy to see why this happens. Now to dwell more into the fundamental lemma of calculus of variations, first let us consider what is a dot product. Okay, now you may recall doing dot products of vectors, right? So when you write a vector A dotted B, the understanding is that this is I is equal to 1 to n ai times bi. Basically this is a component by component multiplication of the vector components and then addition of all of them. So this is how you may recall you would have done dot products of vectors. But there is a more general definition for what is a dot product. So basically it is a binary operator. Binary operator means it takes two arguments, so in this case two vectors, which takes two objects from a space, say x. So in this case this x was a vector space. Okay, and it gives a real number. So basically this is an operator which takes two arguments from a space x and gives a real number. Okay, this is the basic definition, and then there are some properties that follow. So if we define that this A comma B equal to alpha is a dot product with A and B coming from the space X and alpha belonging to the real line, there are few properties which has to follow. One is the commutative property, which means A dot B and B dot A both are same. Second is distribution over addition, which means A dot B plus C is equal to A dot B plus A dot C. Here C is another vector from the same space X. And third is scalar multiplication, which means alpha times A dot beta times B is alpha beta times A dot B. And you can visualize that for vectors, all of these properties are followed. So any operator which takes two such arguments and gives a real number, and that can qualify as a dot product. Now for vectors, you are already aware of this definition. Okay. Now next, the question is to think beyond this particular definition of a dot product from the basic properties, and to ask a question that let X denote a space of functions, not a space of vectors, but a space of functions, which are differentiable at least once. And this is just an example. We can take any set of functions for a particular objective. And let's say these functions are f of x and g of x, which come from this space. Now, and let's say these are all finite within the domain 0 to 1. So if we define alpha, a scalar, a real number, equal to the definite integral 0 to 1 f of x times g of x, does this form a dot product? Or does it satisfy the properties of a dot product? Okay. Which means is f comma g equals to g comma f? Of course the answer is yes, because integral 0 to 1 f g dx is same as integral 0 to 1 g f dx. Okay. Similarly, you can check the other properties and you will realize that this indeed is a dot product. Okay. Now let's see what does fundamental lemma of calculus of variations say. Now here we will not do a mathematically rigorous definition. We will use what we really need for our purpose. Okay. So what it says is that let f of x be a given function. Given means it is given fixed. And let g of x be an arbitrary function. Arbitrary means you can take any form for that function. So then what this fundamental lemma says is that if integral 0 to 1 f of x g of x ds is equal to 0, this has a both way implication of f of x being identically equal to 0. Okay. Now this integral 0 to 1 need not always be 0 to 1. Basically the idea is that whichever domain we are looking at, it is defined there. But the basic idea is that if a given function times an arbitrary function's definite integral is 0, what this lemma says is that that is possible only when that given function is identically equal to 0. Okay. So this will complete the 3 to 1 proof, because we essentially had 0 to 1 u comma xx plus l v dx equal to 0. So this is where we reached. Now if you see what is in the brackets is a given function, because u of x is the displacement field, will be a given function. L of x is a force field which will be given, and v of x is an arbitrary function. Why is it arbitrary? Because it is basically a virtual displacement, and you can take any form which is kinematically admissible as v of x. So that is an arbitrary function. So from this lemma, this 3 to 1 proof is completed. Now the equivalence of 1 to 3 is also straightforward, and basically it uses something called method of weighted residuals. So let's say, now recall that we will start with 1, which is the PDE form. So we define the residual R of x as u comma xx plus L of x, and we want this residual to vanish throughout the domain. Okay. Now we choose an arbitrary weight function w of x, and you may think about what should be its properties, and you will realize that it will have similar properties as v of x. And if we repose this problem using the fundamental lemma, so what we want is r of x identically equal to 0, which would imply that 0 to 1 w of x, the arbitrary weight function, times r of x dx equal to 0. Okay. And then basically you can expand things and make use of the properties, and eventually you will reach this. Okay. So earlier we started from 1 and reached 3. Now we have, earlier we started from 3 and reached 1. Now we have started from 1 and reached 3. So this proves that the form 1 and the form 3 are identical or equivalent both ways. Okay. And these are some notes which you will see that are in line with what we have discussed earlier. But the process which we have followed in going from 1 to 3 is very, very important. Because this process can basically allow you to take any PDE and convert it to its corresponding integral form. Okay. And in general, this PDE we call the strong form, and the integral form we call the weak form. And why do we have that nomenclature, we will see in a while.